Introduction. Opening shot of a mathematical graph with a complex curve. Welcome to your channel name. In this video, we're going to explore the art and science of curve sketching. Sketching curves is a fundamental skill in calculus and mathematics in general. Whether you're a student learning about curve sketching for the first time or someone looking to refine their skills, this video is for you. Let's dive into the world of curve sketching. 1. The basics of curve sketching. Visual, basic components of a curve. Before we dive into the details, let's go over the basics of curve sketching. When sketching a curve, you'll want to consider key components like the domain, range, and critical points. These elements will guide you in creating an accurate representation of the function. 2. Step 1. Find the domain and range. Visual, identifying domain and range. The first step in curve sketching is to determine the domain and range of the function. The domain is the set of all possible input values, while the range is the set of all possible output values. Knowing these boundaries helps you understand where the curve exists. 3. Step 2. Locate critical points. Visual, identifying critical points on a curve. Critical points are key locations on the curve where the derivative is 0 or undefined. They often correspond to local extrema, maxima, and minima, and inflection points. Calculating these points is crucial for sketching the curve accurately. 4. Step 3. Determine asymptotes. Visual, recognizing vertical and horizontal asymptotes. Asymptotes are lines that the curve approaches, but never touches. There are two types: vertical asymptotes, where the function approaches infinity or negative infinity, and horizontal asymptotes, where it approaches a constant value as x goes to infinity. 5. Step 4. Analyze end behavior. Visual understanding end behavior. End behavior refers to how the curve behaves as x approaches positive or negative infinity. Does the curve rise or fall? Knowing the end behavior helps in sketching the overall shape of the curve. 6. Step 5. Sketch the curve. Visual demonstrations of sketching the curve. Armed with all this information, it's time to sketch the curve. Start by plotting critical points, asymptotes, and using your knowledge of end behavior. Pay attention to any symmetry or repeating patterns in the function. 7. Step 6. Test points. Visual, testing points to refine the curve. To refine your sketch, choose test points within the domain and plug them into the function to determine the behavior between key points. This helps ensure the curve accurately represents the function. 8. Advanced considerations. Visual, additional factors affecting curve sketching. In more complex functions, you may encounter additional factors such as concavity, inflection points, and discontinuities. These elements can significantly impact the shape of the curve and should be considered in your sketch. 9. Practice, 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 practice. Visual, encouragement to practice curve sketching. Curve sketching is a skill that improves with practice. The more functions you sketch, the more comfortable and proficient you'll become. Don't be discouraged by initial challenges. Keep practicing. Conclusion. Visual host summarizing key points. In conclusion, curve sketching is a vital skill in mathematics that allows us to visualize and understand the behavior of functions. By considering the domain, range, critical points, asymptotes, and other factors, you can create accurate representations of complex curves. Closing shot of a mathematical graph. If you found this video helpful and want to see more math-related content, please give it a thumbs up and consider subscribing to our channel. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and happy curve sketching. Introduction. Opening shot of a mathematical graph with a function curve. Welcome back to your channel name. In this video, we're continuing our journey through the world of calculus by diving even deeper into the concept of differentiation. If you've already grasped the basics, get ready to explore more advanced techniques and applications of differentiation. Whether you're a calculus student or just curious about the power of derivatives, this video is for you. Let's delve further into differentiation. 1. The power rule. Visual equation for the power rule and examples. First, let's review the power rule. It's a fundamental differentiation rule that allows us to find the derivative of a function like fx equals xn, where n is a constant. The power rule states that fx is equal to an x n1. It's a handy tool for differentiating polynomial functions. 2. Product rule. Visual equation for the product rule and examples. Next up, we have the product rule. This rule is used when you need to find the derivative of a product of two functions. It's a bit more involved, but extremely useful in various scenarios. Remember, it's u v prime equals u times v prime plus v times u prime. 3. Quotient rule. Visual equation for the quotient rule and examples. The quotient rule comes into play when you need to differentiate the quotient of two functions. It helps us find the derivative of uv, where u and v are functions of x. The quotient rule states that uv prime is equal to vu, uv v squared. 4. Chain rule. Visual equation for the chain rule and examples. Now let's tackle the chain rule. It's a powerful rule used when functions are composed within one another. The chain rule helps us differentiate composite functions, and it's often applied in scenarios involving nested functions. 5. Implicit differentiation. Visual examples of implicit differentiation. Implicit differentiation is a technique used when functions are defined implicitly rather than explicitly. This often occurs when equations involve both x and y. By differentiating both sides of the equation with respect to x, we can find dx. 6. Higher order derivatives. Visual explanation of higher order derivatives. Derivatives aren't limited to just the first order. You can take higher order derivatives by differentiating a function multiple times. For instance, the second derivative, denoted as f, represents the rate of change of the rate of change, and so on. 7. Applications of differentiation. Visual, real-world applications involving differentiation. Differentiation isn't just a mathematical concept, it has numerous practical applications. Engineers use it to analyze motion, economists apply it to marginal analysis, and scientists employ it to study rates of change in various phenomena. 8. Optimization problems. Visual examples of optimization problems. One exciting application of differentiation is in optimization problems. These are real-world scenarios where we want to find the maximum or minimum value of a function, like maximizing profit or minimizing cost. 9. Newton's method. Visual explanation and example of Newton's method. Lastly, let's touch on Newton's method. It's a numerical technique that uses differentiation to find the roots of equations. It's particularly useful when solving complex equations that can't be solved algebraically. Conclusion. Visual host summarizing key points. To wrap it up, differentiation is a powerful tool in calculus, with various rules and applications. It's not just about finding slopes. It's about understanding how things change and optimizing outcomes in the real world. Closing shot of a mathematical graph. If you found this video informative and enjoyed diving deeper into the world of differentiation, please give it a thumbs up and consider subscribing for more math and science content. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and keep exploring the incredible world of calculus. Introduction. Opening shot of a mathematical graph with a continuous curve. Welcome back to your channel name. In this video, we're delving deeper into the world of calculus by exploring the concepts of continuity on an interval and differentiation. These ideas are fundamental to understanding how functions behave, and how we can analyze their rates of change. Whether you're a student tackling calculus for the first time, or someone looking to expand your mathematical knowledge, this video is for you. Let's dive into continuity and differentiation. 1. Continuity on an interval. Visual graphs illustrating continuous and discontinuous functions. To start, let's talk about continuity on an interval. A function is considered continuous on an interval when you can draw its graph without lifting your pencil. In other words, there are no gaps, jumps, or sudden breaks in the function. 2. Types of discontinuities. Visual examples of different types of discontinuities. There are different types of discontinuities, such as removable, jump, and infinite discontinuities. Removable discontinuities can be filled in to make the function continuous, while jump and infinite discontinuities involve abrupt changes in the function's values. 3. The intermediate value theorem. Visual diagram illustrating the intermediate value theorem. The intermediate value theorem is an essential concept related to continuity. It states that if a function is continuous on a closed interval, a(b), it will take on every value between φ and fb at some point within that interval. This theorem has practical applications in various fields, including science and engineering. 4. Differentiability. Visual graphs of differentiable and non-differentiable functions. Now let's move on to differentiation. A function is differentiable at a point x if it has a well-defined derivative at that point. In other words, it's smooth, and you can find its rate of change at that specific point. 5. The derivative. Visual equation for the derivative. The derivative of a function fx at a point x is represented as fx, or dx. It tells us how the function's output changes concerning the input as we move very close to that point. 6. Calculating derivatives. Visual, methods for calculating derivatives. There are various techniques for calculating derivatives, including the power rule, product rule, quotient rule, and chain rule. These rules allow us to find the derivative of more complex functions by breaking them down into simpler parts. 7. Interpretation of the derivative. Visual, graphical interpretation of the derivative. The derivative also has a graphical interpretation. It represents the slope of the tangent line to the curve at a specific point. In other words, it tells us the rate at which the function is changing at that point. 8. Applications of differentiation. Visual, real-world applications of differentiation. Differentiation has countless practical applications, from calculating the velocity of an object in motion to finding the minimum or maximum points of a function in optimization problems. It's a crucial tool in various scientific and engineering fields. Conclusion. Visual host summarizing key points. To sum it up, continuity on an interval and differentiation are fundamental concepts in calculus. Continuity helps us understand how functions behave within specific intervals, while differentiation allows us to analyze their rates of change. These concepts are the building blocks for more advanced topics like integration and differential equations. Closing shot of a mathematical graph. If you found this video informative, please give it a thumbs up and consider subscribing for more math and science content. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching your channel name, and keep exploring the fascinating world of calculus. Introduction. Opening shot of a mathematical graph with a function curve. Welcome to your channel name. In today's video, we're going to explore two fundamental concepts in calculus: functions and limits. Whether you're a student just starting your calculus journey, or someone looking to refresh their understanding, this video will provide you with a solid foundation. Let's dive into the world of functions and limits. 1. What are functions? Visual graphs and equations representing functions? First, let's talk about functions. A function is like a mathematical machine that takes an input, performs some operations on it, and gives you an output. It's often represented by an equation, such as fx equals x squared, where x is the input and fx is the output. 2. Function notation. Visual, examples of function notation. We use function notation to describe functions. In fx equals x squared, f is the name of the function and x is the input variable. The output of the function is fx, which is also referred to as y in traditional graphing. 3. Graphing functions. Visual, graphs of different functions. Functions can be graphed on coordinate planes. Each point on the graph represents an input-output pair, and the curve connecting them shows how the output changes with the input. 4. What are limits? Visual, illustration of approaching a point on a graph. Now let's move on to limits. A limit represents the value that a function approaches as the input gets closer and closer to a particular point. It's like asking, what happens to the output as we get very close to a certain input value? 5. Limit notation. Visual examples of limit notation. We denote a limit with notation like limxa, fx, whereas the point we're approaching, x is the input variable, and fx is the function. This notation tells us which value the function approaches as x gets closer to a. 6. Evaluating limits graphically. Visual, graphical representation of evaluating limits. To evaluate limits graphically, we look at the behavior of the function as x gets closer to the specific value. Does the function approach a single value or become undefined? Graphs can help us visualize this. 7. Evaluating limits algebraically. Visual, algebraic techniques for evaluating limits. We can also evaluate limits algebraically. This involves simplifying the function and substituting the value into the expression. If we can't substitute directly because it results in an undefined form, we can use algebraic techniques like factoring or rationalization. 8. The concept of continuity. Visual, continuous and discontinuous functions. Continuity is an important concept related to limits. A function is continuous if its graph can be drawn without lifting the pencil. This means there are no jumps, holes, or gaps in the graph. 9. Practical applications. 2000. Visual, real-world examples involving functions and limits. Functions and limits are not just theoretical concepts, they have real-world applications. Engineers, scientists, and economists use calculus to model and solve problems involving change and optimization. Conclusion. Visual host summarizing key points. To wrap it up, functions and limits are foundational concepts in calculus that help us understand how things change and behave mathematically. They form the basis for more advanced topics like derivatives and integrals. Closing shot of a mathematical graph. If you found this video helpful, please give it a thumbs up, and consider subscribing for more math and science content. If you have any questions or specific topics you'd like us to cover in future videos, please leave a comment below. Thanks for watching Your Channel Name, and happy learning!